This is a session on work that's done by two faculty at Oregon Institute of Technology out in Klamath Falls, Oregon. And even though UFON is our only audience at the moment, this is being recorded. And so we hope that all of you who are watching will enjoy it. The first speaker is Tiernan Fogarty, and he's going to talk about the basic beam equation modeling exercise that he's worked on with his students. So Tiernan.
Okay, thanks. Yeah, thanks for having me. I haven't tried one of these virtual things before. So I should have put Jim's name on here also. Jim's going to talk next, and he's kind of gone in a little bit different direction, but we've both worked on this quite a bit. So I'm going to start just with an overview of what I'm going to talk about. But you want to keep in mind that what the students will see doesn't really start till slide 11. So I want to introduce the problem and the motivation a little bit. And I used to do this with the students, but now I don't really give them any heads up, except we're going to do a project and we just start out with data collection. So even though I'm going to introduce the system and the beam equation and all that here, I don't do that anymore with the students first. It just seemed to be a little confusing to swap back and forth. So then I'll go over the beam equation with you guys, and then try and motivate why we're doing this a little bit, and then talk about how we set up this exercise, and then we'll go through solution techniques and student work. All right, so after we've taken data, then we'll talk about this, but I no longer do this first. But here's the beam equation. So if we just have a bending beam, and I have one right here, maybe it'll show up on the camera. It's just a piece of molding from Home Depot, and it bends pretty easy, just under its own weight, and it's really easy to get. It's pretty cheap. I have a bunch of them. So when I do introduce the equation to the students, most of them have had vector calculus, and if they haven't, they can pick this up right away. So I just start with the curvature. So I have this equation for curvature that a lot of them have seen, and if they haven't seen it, it's not too hard to get them on board with this. And then if we take the small deflection approximation, that equation simplifies a lot, and the curvature is just the second derivative of the displacement. So I've read about this a lot, and it seems like all the engineers say that it's a valid technique as long as, I don't know if you can see how much this bends, but as long as the slope at any point is like less than 1/10 of the length. So if it doesn't bend too much. And on some of the experiments that we run, it might exceed that a little bit, but it still turns out that the model works extremely well, even if we are maybe going a little bit past this small deflection approximation. It's okay that it's a little bit messy. They still learn a ton. Okay, and so to continue, we need to introduce this thing called a bending moment, and it's just a reaction induced when this external force, in this case of gravity, or maybe a load that's on the beam, is applied. And I guess I think about this bending moment as a balance of forces that appears inside this beam under the load, right? So once this load is applied, the beam deflects, and then it stops deflecting, and there's a whole bunch of, you could think of it as a vector, pointwise vector of forces inside the beam that stopped this deflection. So this is called the bending moment, and we're going to need that to get further. So the bending moment is dependent on two things. One of them is what the rod is made out of. So that's the right, things like 8 feet long. So that's the E, right? It's a constant that has to do with just the properties of what the thing is made of. And then I is the cross section. So in one direction, it's very thin and it bends very easy. But if I flip it sideways, even though it's the same material, it's much thicker. It doesn't really bend at all, just because of the, oops, where's my camera? The difference in the cross section. One way bends easy and the other doesn't. So when I flip that beam, the I would change, but the E would not. So those material properties go into this bending moment. So it depends on the curvature, Young's modulus, and the moment of inertia, which is measure of this cross-sectional area. And if I multiply those two together, I get a thing called flexural rigidity, which we don't really need, but it does come up if you're looking in literature for this sort of a thing. If you're reading about beams, you'll read about that. So it's just a combination of these two parameters. So then we still want to get to the governing equation. The bending moment is related to what's called the load per unit length. It's just the weight per length. And that equation, hopefully you can see it, the second derivative of m with respect to x equals the weight per unit length. I don't think that's necessarily an obvious thing at all. It's probably the part of this whole thing that I understand personally the least. You can derive it using the mean value theorem in calculus. It's just a force balance thing, but I don't go through it in class because it would just take an extra day or two, and I don't know that it would really help them in a differential equations class. It's kind of a non-trivial derivation of that equation. Luckily for me, my office is right next to 3 civil engineers, so I can talk to them about this a lot, and they referred me to calculus and the mean value theorem about this. They didn't really have a great explanation either. All right, so if we buy that the second derivative of the bending moment is equal to the weight per unit length, then I can substitute in our previous relation for the bending moment with regard to curvature. And as long as Young's modulus and the cross section are constant, all these, this E and I, as long as they're constant, we can end up with this governing equation, which is 2 constants times the fourth derivative of the position is equal to the weight per unit length. And there are all these constants, and I do spend some time talking about these with the students, but only after we've collected data. So I don't do any of this until after they've got data and they've got to mess around with these things.
So, yeah, what I see is that I finally see why it's a fourth derivative, because k is the second derivative of y, and you're taking the second derivative of k, and that's why you get a fourth derivative. So
yeah,
okay.
Yeah, it took me a while to figure all that out, honestly. Yeah, and the thing that's the most mysterious to me still personally is this the second derivative of the bending moment m is equal to the I did find somebody sent me a nice video on YouTube where someone explains it, and it does just use some calculus in the mean value theorem. It's a lot like deriving the integration for the wave equation on a string. But it's not trivial at all, and so I don't go through it with students. I just ask them to
accept.
Believe me, yeah. Otherwise, we just don't have time for everything, right? Unfortunately. Okay, so in terms of what we do, I start with the students. I just tell them we're going to do a project, and we pick teams, and then I come in with all the stuff, and they all have to be there that day. And so I don't show them this governing equation, but I mean, I guess since we're all here in this conference, everybody's on board with this idea. I mean, the whole idea is to just start with data collection, and then hopefully come up with this governing equation. And then we'll go back later and talk about deriving it, which is totally different than how I do the mass spring or the RLC circuits, where I kind of draw some little pictures and ask them to accept a bunch of stuff, and I get these equations and then tell them how to solve it. And we don't really do any science at all. It's just, here's some stuff, and here's how you can solve it by doing what I do. And it's not really all that satisfying. I'd really like to do more of this. I just still haven't figured out how to deal with the time constraints. And I even wrote up in Simiode one of these mass spring approaches similar to what I'm doing with the beam, but I haven't figured out how to do that either, at least where we are. I don't have the equipment, and I just haven't, Jim and I have talked about it, but we haven't really ever put it together yet still. So anyways, we contrived this data collection exercise, and then the students just throw the data into Excel, and hopefully the idea is that just looking at this raw data, they'll come up with what we want to get to, which is this beam equation. So it's just a different approach. If you haven't tried it yet, it does work really well. They seem to really like it. But you have to put a lot of thought into it first. Otherwise, you can spend a lot of time and really not really get anywhere. So I guess this is more of my personal ulterior motives. I want them to really think about science as a process and think about the scientific method. And we don't have time for any of these things. Usually when I'm running through calculus or doing differential equations, we just kind of tell them to do what I do, and here's how I do it. And I'd really like to do a lot more of this, getting to the why of things. But we do have a certain amount of content we have to cover in a brief amount of time. So you have to make sacrifices, I guess. But I've always managed to at least get this one experiment in. And if I could come up with another really good one, I would like to do that also. At least one that I could do. There are a lot of other really good ones. I just haven't pulled any of them off yet. Right. So at least where we work, we have some, I guess, location specific things to worry about. Most of our students are civil engineering and mechanical engineering by the time they get to this course. There's a few electrical engineering. And we do have really nice labs where they do buckling columns, and Jim and I were able to take these materials over and measure these constants with some of our students. And so a lot of these students have seen this, or at least heard about or thought about this idea of a hanging beam. It seems like a buckling column would be another good one to do, but I don't have a good way to do it yet. I mean, we've tried a couple things. So if anyone has an idea, I would love to get an email about, oh, you could do it like this. Like, I just don't have a practical way to squish a column and measure both the deflection and the force. And we do have really nice labs where they do that outside of my classroom. All right, so I guess this is just about it. We're gonna get into it, but if you wanted to do something like this, all you have to really do is do it ahead of time, maybe with one other person. Jim and I ran through this, and another colleague of ours and I ran through this previously. And if you run through it once or twice, and you let the students know it's coming, you don't really have to tell them what they're going to be doing specifically. Just show up and be ready. And as long as all the required components are there, which aren't that much. I have 4 of these beams, and I've managed to run it with 36 students in 1 hour. You just have to bring the bending beams and a few tables to bend them between, and maybe some calculus books to hold them down, and a scale to weigh them, and then a ruler to take measurements and some paper. So you can get all that together by yourself in an hour or two, and run in there right before class starts and make it happen. All right, and these are the 3 cases that we look at. They're all easy to do. I can just rest one beam between a couple of tables, and that's the upper example pinned, and I can hold a beam almost just like this ruler. I can just hold it, but if it's longer, it just bends under its own weight. Stick a couple calculus books on top of it, and then the embedded is really easy. I put it between 2 tables and then put some books on it, and students have no trouble, and we get surprisingly good data. At least I think we do. I'm pretty amazed at how well this works. So this is what they start with. I give them these big sheets of paper and a couple of tables and a beam, and tell them to do a few things in particular. So I want them to put the beam in these 3 different configurations in front of this paper, and then just measure the deflection from horizontal, from the horizontal line that goes between the top of the 2 tables. And they also have to weigh the beam. We're going to need that. And they have to measure the beam's cross section, right? So I guess you can't see that, but we need to measure really the end of the beam, how long it is and how thick it is. Not the length doesn't really matter, but the cross section we need. So they measure all that stuff, and it doesn't take that long. And Jim, luckily for me, provided me with a couple of pictures of students doing this. They just hang this paper up between a couple tables. They put the beam across. There's our calculus books to hold it. And while it's there, they make a bunch of marks on the paper. And then after they have their marks, they move the beam, and then they start measuring stuff. And then they just have a bunch of raw data. And all they all know how to use Excel. And they just throw it into Excel and try and do a curve fit. This one didn't turn out that great, but they're able to analyze it almost immediately. Like later that day, outside of class, a lot of them will send me an email with all the data in Excel and curves fit, and that's enough to really get them started on their own. They start thinking about, why is this kind of curve? And then I do give them some, I guess you'd call leading questions. It turns out, at least the times I've done it, the best fit curve is either fourth order or sixth order. I still haven't really figured out the sixth order. But I asked them to think about, well, if there's a lower order, it's probably better to start with that. And is there a single degree fit that works for all three? And the fourth order definitely fits all three. And then, since it's a differential equations class, I want them to think about, what kind of differential equation might that fourth degree polynomial be a solution of? And I don't have to give them this. I mean, eventually I do, but it's not that big of a jump to speculate that it's just some order of differential equation. Some of them choose 6, some of them choose 4 based on how their data came out. And then we start talking about constants, which leads to boundary conditions. So this polynomial on the top is really what they have measured, right? They measure the deflection, and they get numbers for C over 24 and A over 6 and B over 2. I mean, if I just integrate that governing equation, I get this polynomial, but that's what they start with. The students start with that polynomial, and all those constants are things that come out of fitting that in Excel. And then we can start talking about taking derivatives, and all the derivatives have a meaning that's, at least in the beginning, not too hard for them to figure out. The first derivative is the slope, and the second derivative is curvature. Most of them don't know what shear or load is, but it's not too big of a leap if you try and explain what shear is, why the third derivative is important. And the fourth derivative is the load, which is really just the governing equation there. And when I talked to one of my colleagues next door, they don't do it this way. They do it the opposite way. So if you want to get into this and you're looking around, you might find this. I used all the same letters that the civil engineers use. So they just start with a distributed load and then start integrating. So one integration is the shear, 2 integrations is the moment, and then the slope. And then eventually they get, after integrating 4 times, 4 integration method, they get up to the displacement. Just a different way of thinking about it that I hadn't thought about, but I kind of like it. I haven't shown my students this yet, but we're going to do this next week. Unfortunately, the timing is off a little bit. I haven't done this in a year and a half because of COVID, but we are doing it next week, and I'll get to go through this all again with them. All right, I don't know how am I doing on time, by the way? Oh, I'm doing fine. Okay. So so once we start trying to figure out solutions that they can compare with their best fit curves, they have to start worrying about how many constants, right? So if we have a fourth order polynomial and I integrate 4 times, I'm going to get 4 constants, and we need to figure out some sort of other piece of information to find those 4 constants. And some of them really power on with the 6th order. They occasionally, I don't know why, but occasionally they'll get a better fit. It's a 6th order polynomial, and they're convinced that it's a 6th order differential equation. But then once they integrate 6 times, it's really kind of impossible to come up with 6 conditions to get those constants. But I try not to really help too much unless they've really tried something and get to that point, which does happen sometimes. Anyways, with the embedded, it's not too bad to come up with these conditions, right? Because we know that at each end, the derivative is 0 and the displacement is 0. So there's 4 conditions right away. And I encourage them all to try this case first, to try and come up with a theoretical solution to match with their best fit curve, and then to move on to the pinned. It's still the same governing equation. There's still 4 unknown constants, and even though it's probably obvious to us, like what the displacement is at each end, for some reason it's not obvious to the students. And the inflection points are not obvious. I mean, none of the boundary conditions, at least in my experience, are obvious at all to the students. So they do pretty well with the embedded, because they can see that it really has a zero slope tangent line. And for some reason, when you're holding it down, they realize, yeah, it's set at zero, the height is zero. But when the rod is free to bend like this at the edge of the table, they don't tend to obviously just say, oh, it's still a height of zero. I don't know what happens. Maybe they look at the end of the rod or something, but so this is usually harder than I expect for students. I have to talk about how to get these 4 conditions, but the height is still zero, even though the rod isn't, or the beam isn't flat at the end, and the first derivative is zero, but that's not obvious to them at all. So I think that's kind of a good exercise to let them struggle with a while. I mean, they know at this point that there are 4 conditions they need, but they mess around for a while before they get them. And the last case is definitely more difficult. They get 2 right away because they've already done the one embedded end. But the free end, we spend a lot of time talking about that, and we've had great discussions about what happens at that free end and how do we get 2 conditions out of that free end. And I usually, well, not usually, I always just end up having to tell them that there's this thing called shear, and that at the free end, since there's no beam beyond the end of the beam, there's no shear right at the very end, which means the third derivative is zero. But I definitely let them mess around and struggle with that, like for a couple of days at least, because that's how they learn things, at least in my experience. I know I'm preaching to the choir here, but I really enjoy the conversations and the discoveries that students have had just trying to figure out these boundary conditions. And it does let us introduce a little bit more physics than we normally would if we just kind of did this with the textbook approach. All right, I might get done early, but I don't know. All right, so what do I expect from them? I put them into groups just for time purposes. I can't have 30 people all do it individually. They seem to work better in a team anyways, 2 to 3 people, maybe 4 if I have a really big class. So as a group, I want them to come up with this self-contained, well-written report, and they have to have data for all 3 scenarios and best fit models. And then I want them to solve the differential equation and compare their theoretical solutions with their measured solutions, and then do some sort of error analysis. And I really leave that up to them, how to convince the reader that they've done some sort of error analysis. I don't really help with that, but they have data and they have these 2 different solutions. So the bottom 2 equations are, all that's supposed to be is that the top one here, they measure all those constants, C, A, B, lowercase c and d. Those are all measured in their best fit from their data. And then if I take just one of the scenarios and solve it, I know what those things are. I know the length of the beam, I know E and I and W. And so I can compare these 2 things directly. And that's what I want them to do in all 3 scenarios. And then try and convince me that they've done some sort of numerical comparison, some sort of error analysis. And I've always been extremely pleased with what they come up with. Nobody ever just turns in a bunch of junk. They really go out of their way. And every time I've done this, I've been amazed really at the work that they've turned into me. And then I ask them to also use this. It used to be extra credit, but now it's just part of the assignment. I want them to estimate Young's modulus just from their data.
Take about another minute or so, okay?
Oh, is that? Oh, I'm sorry. I thought I had 6 more minutes.
No. Well, take a 3 of the 4 of them. Go ahead.
Okay, so I'll be quick then. Thanks, Brian. So if you try this, you might encounter this. I have encountered it, although Jim says that he's figured it out. But we've had big problems, at least I have, when they measured in centimeters, and then when they measured in meters, it seemed to work just fine. I thought I had, Jim and I talked about that. Maybe it had something to do with this condition number that comes out of this. Anyway, so these are things that you could maybe give extra credit for, although I do require the Young's modulus now as part of the assignment. And I talked about this a lot since I'm down to a short time. They measure the height and the width of of the beam so that they can get the moment of inertia. They measure the weight, they measure the length. So they have all these constants, W, C, I, and this W over 24 CI is a number that they have measured in their best fit, so they can use it to approximate E. And then a bunch of groups did that, and here's a bunch of listed numbers. I took this plastic beam over to my neighbor, and he was able to use the barcode to look it up online. I say I, but it's really my colleague found that according to Home Depot, it has a Young's modulus of 4.0 gigapascals, and the numbers that my students got were between 1, 3, 9. One of my teams looked it up, and they found a different number online of 4.9. So they're all right in the ballpark, even with what I'm pretty sure is a clear violation of the small amplitude approximation, but it still works out really well, and it's pretty satisfying to see all this. All right, so if the 1040 was my time, I'll stop, but they love it. At least in my experience, the students really like this. They wish we would have done more, and I really do want to do more. I got kind of derailed, like I guess we all did the last couple of years, but I'm really looking for another one. I'm looking forward to doing this next week. I'd like to have like a bank of projects, and I could just kind of swap them in and out every time I taught it. So that's a big reason that I'm part of this conference.
Well,
okay, so I guess that's it. Thank you.
Thank you very much, Tiernan. Can you go back to your spreadsheet just quickly?
Sure. You're not supposed to look at that. It's really
Okay.
bad.
No. All that's in here is for one of these configurations. You've measured the distance from one end and the deflection. That's it. There's no motion detections. It's
no. It's just literally. I don't know if you can see it, but
yeah. But that's just one.
It's just hanging there.
Yeah.
They put a piece of paper behind it.
Yep.
And they measure, from horizontal.
Okay.
And they put those numbers into Excel, and then they're able to just do a best fit polynomial.
Okay, so the point is that it's a very static experiment. They don't need expensive equipment, and they can measure those deflections. Okay, that's great.
I think it cost me, I don't know, $15 to get this plastic molding.
Okay. Well, thank you very much, Tiernan.